Hi everyone and welcome to this my video on polar form of a complex number. Yes, it's part of the VCE specialist maths course here in Australia, but it doesn't matter because it's actually universal. This stuff is worldwide because maths is a constant. That joke never gets old. Yes, it really does. I'm going to stop using it from now. My name's Darren from Maths Guru. Thanks very much for joining me. Hopefully you've been watching my previous videos. If not and you are new, can you do me a massive favor and subscribe? Very few people watch maths videos. And I sit in this room talking to myself like a lunatic, hoping to be of help and value to people out there. All right. So if you can, that would be great. It just sends me that message and say, yeah, I'm watching. Thanks very much. Behind me are our learning objectives. Let's understand what it means by polar form, understand what it means to be the non-uniqueness of polar form, know how to find the complex conjugate in polar form, and know how to use the CAS to solve equations. And again, I say this every single lesson. Your CAS use is going to be critically important to this particular topic because using a CAS is going to make life much, much easier. Now, in the previous two videos, we've looked at all sorts of stuff, the basics of complex numbers. We've looked at multiplication and division. We are looking at all of the building blocks because they become really important towards the end of this particular section. Learning those building blocks well, massively important. And if you haven't already done so, do as many questions as you can. It's not about proving your mathematical dominance, although that's lovely. Getting everything right means you're not learning anything. So you want to find questions that trip you up, all right? Because that means you're going to go, oh, hold on a moment, I didn't understand that properly. That's important, right? Now, Argand diagram's really important. It's a visual representation. And I talk over and over again about how geometrically, if you can visualize what this stuff means, it can make life a lot easier. That's what we argue in methods. You know, methods, I say for every single question, sketch the graph, even if it doesn't matter, even if they don't ask for it, sketch the graph, because believe it or not, you could find out there's a trick in there that by sketching it, you're like, oh, okay, that's much easier. Right, we're going to look at polar form. Now, polar form is basically nothing to do with polar bears. I couldn't help myself with that joke, all right? But again, what fascinates me in mathematics is in the United Kingdom, we had a guy called Barry. Barry sat in a room on his own. He had bad facial hair, a bit of a hump, a lisp. He had no windows, no friends whatsoever, and basically a Sudoku, right? That was Barry. Yeah, bless his little cotton socks. And Barry's job in the United Kingdom was to make maths as complicated as it could possibly be. No, not the actual maths, just all the stupid words that describe it. So, for example, why is it we have multiply, product, and times all mean the same thing? That's why people find maths confusing. It's because of the language, not actually the maths. Now, obviously, we locked Barry in that room and threw away the key, and he will never, ever come out again. We've severed his communications. Maths in the United Kingdom, hopefully, is a little bit easier. But basically, believe it or not, there are two ways of describing polar form. Yes, we can describe it as polar form, and we can describe it as modulus argument form. Again, two things, two completely different words that mean the same thing. Sheesh. Right, let's make it real. Lol. All right, that was a really bad complex numbers joke. Polar form. We know, as I say here, that we can represent a complex number, or a complex, number as a coordinate on an Argand diagram. All right, so Z equals A plus BI, which is our standard form, can be represented here. Oh my goodness, why do I keep doing that? Here as a point on an Argand diagram. We know that if it's A plus BI, that means that this distance here is A, and this distance here is B, and that must be some angle of theta with respect to an anti-clockwise movement from the x-axis. Okay. Now, we've seen in previous subjects that we can re-express that value of A as equal to R cos theta. And our value of B would be equal to R sine theta. Now, again, that's nothing more than basic trigonometry, because if I know this angle here is theta, and that's my hypotenuse, and that's my opposite and hypotenuse are linked by sine, so in which case we'd end up with B is equal to R sine theta, and A is equal to R cos theta. And substituting that in would suggest that Z, therefore, could be equal to R cos theta plus R sine theta times I. And believe it or not, that's polar form, I know, or modulus argument form. Yes, but that's polar form. It's written now with respect to some angle with respect to the x-axis rather than a horizontal and vertical distance. Okay, or a coordinate. All right, so there we go. Now, sadly, your CAS calculator doesn't have a nice, easy way to put that in. All right, wouldn't it be lovely if it could do that? We could do all sorts of calculations. Well, it sort of does, and I'm coming to that in a moment. We don't want to keep writing this. That is such a long thing to be able to do. Yes, so we can abbreviate that by saying that z is equal to r times the CIS of theta. So CIS of theta. Is there a nice way of remembering that? Well, C comes first, cos comes first. The rest of it must be sort of make sense in sense of, yeah. So there we go. So now Z is equal to R, which is my radius of that point from, if it's set on a circle, from the origin, and theta is my movement in an anti-clockwise way around from the x-axis. Now we get the size of the angle is called the argument of Z. All right. So the size of the angle here is called the argument of Z. Now, there are two ways of saying argument. There's little a, arg of Z, and then there's also a capital arg of Z. We'll come back to that in just a moment, all right? So, now, your CAS doesn't have a nice, easy way. You cannot type into your calculator RCIS theta, so 2 CIS, I don't know, pi on 3, for example, and it knows what to do with that. But theory that's way, way, way outside this course has suggested that r cis theta is exactly the same as r times e to the power of I theta. So now, if I had r cis theta as, let's say, 2 cis pi on 3, and I want to put that into my calculator, I can type that in as 2 e to the power of pi on 3i. And again, maybe one day I'll do a video as to why, but it's way beyond what you need at this moment in time. But it is important to say, hey, well, we can actually do that if I need to using my calculator. All right. Where did modulus argument form come from? Well, again, we know that when we've done previous theory, r is equal to the modulus of z. Yeah, so we know that that distance, if we go back to my diagram here, this distance here is effectively a squared plus b squared square rooted. And so we can define that the radius is equal to the modulus of z. And argument, well, we just had that idea there that the argument is an angle that is measured anti-clockwise from the x-axis. All right, so how does this fit here? Well, these are examples of modulus argument forms where we've got 2 cis pi on 3. Now that 2 basically means that that has a radius. So this distance from here to that point there is 2. And again, if we can see for reference, they've actually written on 2. So there's 2, 2, 2, and 2. Again, 2, 2i, minus 2, and minus 2i because of the real and imaginary. But again, the thing I've noticed with exams is that these divisions here are actually really, really important. Yes, because we now notice there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12 divisions. So between pi, all of those are pi on 12s, and you're going to say, why is it pi? Because there's 0, that's pi on 2, there is pi. So if we know that that has 12 divisions, each of those is pi on 12. 2 of those divisions, therefore, will give me pi on 6. And those divisions come in really, really handy with VCAA exams that I've seen over and over and over again. One other word of sort of highlight for things that are to come is the idea that that's a distance, right? And you can find distances between points. Now, trying to find a distance between those 2 points, a little bit more complicated. Distance between those 2 points, a little bit easier. But again, VCAA come up with sort of confusing questions that basically relate to the idea that you can find the distance between 2 coordinate points. Moving on. Right, there is more than one representation for r cis theta. Because we know that sine and cosine go on and on and on to infinity and beyond. So it would make sense that actually cos theta could be expressed as cos of theta plus 2m pi, where n is basically in all of our integer values. Likewise, sine of theta plus 2m pi, again, basically just takes for the fact that this thing repeats every 2 pi, all right? So we can now write that z is equal to r cis theta can also be rewritten as r cis theta plus 2m pi. That just says there are an infinite number of solutions to the way we could write a complex number in terms of the number of times we're going around a circle. Now, this is what's important. There is something called the principal value of the argument, and that is written as arg of z. That capital A means that the value of theta must fall between pi and minus pi, all right? So it's inclusive of pi, but not inclusive of minus pi. And again, that's written here. So in an exam, you've got to be very careful that if they ask you for capital A, they are looking for the value between minus pi and pi. If it's just a little a, well, again, it can be any, multiple of 2 pi of that value there. All right, what about the complex conjugate in polar form? I said that I knew you were wondering about this. No one was, right? All right, so the complex conjugate, if I know that this is r cis theta, it makes perfect sense, I hope you realize, that if that there is going around clockwise and is positive theta, that is why that is theta, that therefore must be r, he says, cis minus theta. All right, because if we're moving around in a clockwise direction, that would have to be minus theta. And again, the idea that if z is equal to r cis theta, the complex conjugate of that is r cis minus theta is used over and over and over and over again. Right, find the modulus and principal argument of each of the following complex numbers. Right, again, looking at the idea here of a set of axes, because again, I do like to be beside the seaside. No, I don't. I hate the sand. As my daughter will tell you, bless her little cotton socks. Right, okay, find the modulus and principal argument. Now, the modulus is the distance from the center. So if I was to plot that, that's going to be there as 4. So in which case, my modulus of 4 is basically just going to be 4. I know that sounds really stupid, but that's my distance, okay? My arg, the principal argument, so the arg of 4 is basically going to be equal to 0. And you're going to say, why? What angle have I moved from my x-axis to get to that point? 0. Okay, so that's my first one. What's my next one? Minus 2i. We've got this one here. So that's negative 2i. So my modulus of minus 2i is basically just going to be 2, because my distance from the center there is 2 units, not minus 2. That doesn't make any sense in any way, shape, or form. What is my arg? All right, of minus 2i. Well, it's basically 90 degrees. We've moved this way, so it must be minus pi on 2. All right, and again, because it's the capital A, the value has to fall between minus pi, theta, and pi. All right, can't fall any other way. All right, 1 plus I. 1 plus I, that's going to be this one here. So there's 1 plus I there. All right, so we want the distance there. So firstly, our modulus of 1 plus I is basically going to be 1 squared plus 1 squared to square root, which is going to give me root 2. Right, so the distance there is root 2. And again, it's 1 squared plus 1 squared square rooted. And what is my, well, we know that that basically is going to be pi on 4. So my arg of 1 plus I is going to be pi on 4. Why? Because it's got basically 1 divided by 1 tan moving on. All right, so pi on 4. What about the next one? Well, my last one, 4 minus 3i. So we got 4 minus 3i here, 4 minus 3i. Again, to find the distance, so the mod of 4 minus 3i is going to be 4 squared, which is 16, minus 3 squared, which is 9, square rooted, which gives me 5. So we've got a distance of 5. We like that. What about my arg of, what is it, 4 minus 3i? We're going to work out now. Again, I'm just referring to the answer here because that's not one that we can actually work out. So we're going to try and work out what the tan to the minus 1 or minus the tan to minus 1 3/4 is. And apparently that comes out to be approximately minus 0.64 radians. All right, so again, in that situation, we would have had to use a calculator. Find the argument of minus 1 minus I in the interval between 0 and 2 pi. 0 and 2 pi. Argument little a. So let's see what happens there. All right, so a quick pencil sketch of what I've got. Minus 1, minus 1. So let's do that one there. This is minus 1 minus I. Find the principal argument. Well, we know that that sign there is going to be pi on 4. The reason because that's 1 and that's 1. So that's pi on 4. I want it in the interval 0 and 2 pi. So that's pi plus pi on 4, which gives me 5 pi on 4. So my arg of minus 1 minus I is equal to pi on 4. Oh, sorry, try that one again, Muppet. 5 pi on 4. Yes! Right, what's the next thing? Did it say what else I needed to do? Find the argument of. Actually, I'm going to go on because I also want to find the principal argument. So my arg of minus 1 minus I would be equal to, well, we'd have to do this. So it'd be pi, so it'd be actually minus 3 pi on 4. Okay, so again, if I wanted the principal argument there, it would be minus 3 pi on 4. Very important. Right, express minus root 3 plus I in the form r cis theta, where theta is equal to the arg of minus root 3 plus I. Okay, so r cis theta is basically r cos theta plus r sine theta times I. Okay, so we want r first. So we'll work out a modulus of minus root 3 plus I. So root 3 squared is 3 plus 1 is 4. So 3 plus 1, and I want the square root of it, equals 2. So therefore I know my r is equal to 2. So I'm just going to write that there. R equals 2. And then theta. Right, well, they've told me theta here is minus root 3 plus I. I've used my calculator to say that that's basically 5 pi on 6. So in which case my r cis theta would be 2 cis 5 pi on 6. What about the next one? Express 2 cis minus 3 pi on 4 in the form a plus bi. Okay, we can do that because we now know that r is equal to 2 and we know that theta is equal to minus 3 pi on 4. All right, so we know that r cis theta is the same as r cos theta plus r sine theta times I, which just happens to be in the form of a plus bi. Right, r is 2 times by the cosine of minus 3 pi on 4 plus 2 sine minus 3 pi on 4 times by I. All right, okay, so minus 3 pi on 4. So I'm going to draw my unit circle. Thank you very much. Ka-ching, ka-ching. All stations to Canberra. And again, if you know all of these, much respect. But then minus 3 pi on 4 is there. That is pi on 4. Okie dokie. So cos in that situation is going to be negative. So we're going to end up with minus 2 there times the cosine. Well, all stations, so I want the cosine of pi on 4. All right, so there's 1 root 2. There's my pi on 4. Caught a herring, which is 1 on root 2. Plus sine also going to be negative, so make that negative 2 times pi on 4, which again is going to be 1 on root 2. And don't forget the I. I'm going to rationalize the denominators there. So that's going to become minus 2 root 2 on 2. Minus 2 root 2 on 2i. My root, sorry, those 2's are going to cancel, which basically gives me minus root 2, and I. And yes, again, am I overlaboring it? Yes. Have I memorized all of these? No. Can you guys? Absolutely. Your brain power is way better than mine. But again, I also want to show those who struggle a little bit with maths, who are doing specialist maths, maybe for the fun of doing maths, that, you know, actually reverting to first principles and doing that type of stuff isn't a bad thing, all right? If you get the answer, it's fine. Yes, it's better if it gets a bit quicker. But anyway, right. If the arg of minus 1 plus ai equals minus 2 pi on 3, then the real number a is. Now, again, there are 2 ways of solving this. Number 1, bang it in your calculator and solve. It came out with the answer of minus root 3, okay, in which case, yes. But again, if we wanted to go back to the idea of first principles and draw my unit circle, what have we got here? Minus 2 pi on 3. Now, because it's a capital A, that means that that one there is pi on 3. Right, so what have we got here? We got minus 1 plus ai. Well, a would have to be negative for a start, all right? So it would automatically discount that one and that one. So a would have to be negative. Again, if I look at the idea that I've got, what is this? That would be root 3. That's 1, 2, sorry, pi on 3 I should have said, and root 3, well, in which case the only way that that's going to fit in there is if that one there is root 3, and it's going to have to be negative, so A is my answer. And again, lots of people will be able to look at this and go straight away, yeah, it's got to be minus root 3. That's fine, it's okay, but here's another way of doing it, and I'm done! Learning objectives revisited. Know what it means by polar form? Yes. Understand what it means by the non-uniqueness of polar form? Basically, there are way more solutions than just the one, okay, because of that repeating nature of 2 pi. Know how to find the complex conjugate in polar form? Just make the negative, the theta negative, and know how to use the CAS to solve questions. You know, using your CAS for this is really, really important. Thank you very much for watching. Hopefully it's been useful. I've enjoyed doing these videos. If you can like and subscribe, that would be great. Spread the word that this content is there would be even better. But I'm going to record some more videos, and hopefully I'll see you in those. Until then, take care. Bye-bye.